Okay, Chapter 18, Lecture 1, Confidence Intervals for Proportions. Let me make this just a little smaller. Okay, confidence intervals is something you know about. The mechanics for them are quite simple, and it's just an extension on what we did in Chapter 17. Very, very straightforward. They start out talking about coral reefs, and we're trying to get an idea of what percentage of coral reefs are affected by the disease aspergillosis or whatever. Anyway, it's a bad disease. We want to find out how many they have them. Coral reefs, just parenthetically, are extremely important. They're supposedly provide a home for something like 80% of the fish in the oceans or whatever. I don't know. Anyway, they're a big deal. And if they all get sick and die, then that's not going to be good for us. Anyway, so that's why they're studying it. And so the scientists have a sample of 104 sea fans. So let's get this going here. So N equals 104. And they find that 54 of these, so P hat equals 54 out of 104. That's the proportion of the sea fans that they inspected that have this disease. And so that's approximately equal to 0.519 or 51.9%. Okay. Hold on. Okay. Now, it's certainly helpful to know that these 104 sea fans have this disease. We'd like to know, what about P? What about the population proportion? Do all the sea fans in the oceans have this disease in the same proportion? Okay, now, let's say that our sample is random, independent. It's not too big, certainly less than 10% of all the sea fans, and it's not too small. In that NP equals 54 and NQ equals what, 60? Okay, so we're good. We have a representative sample. Therefore, we can use the normal model to describe the sampling distribution of 51 of P hat which equals 54 over 104. Okay? So, but there's a little problem here. Actually, there's a major problem. And the major problem is this. We don't know what P is. In fact, that's why we're doing this. If we knew what P was, if we knew what the true proportion of infected sea fans was, why bother, right? Okay, why do the investigation? Documenting known information is an unrewarding and unrewarded activity. That is, nobody's going to pay you to do it. Okay, but the reason why we're doing this is we don't know. So, and this is, we use, or statistics use, because, you know, the people that do statistics use something called, a standard error. Here we are on the next page. Okay. Now, what, pray tell, is a standard error? I got to make this smaller. Here we go. Okay. Well, what we're going to do is we're going to use, for the model, approximately model distribution, is going to be P hat, comma, square root of P hat, Q hat over N. We're going to use P hat. Now, the reason why we can use P hat to make our standard deviation henceforth called the standard error. As it says in the footnote, it's neither standard nor an error. But as they say, it's shorter than calling it the estimated standard deviation for the sampling distribution. So they just call it the standard error. So the standard error of p hat equals root p hat q hat over n. Okay, so now what are we going to do? Well, we don't know what p is, but we're going to use this. We're going to use our information to estimate where p is, and that's what a confidence interval is. It's an estimation of where where truth lies. And all this thing you've heard, it's plus or minus 5% or 6% or whatever. That number, called the margin of error, that is what we are about to calculate. Okay, so let's calculate this standard error first, because we need this. So it's going to be root 0.519, as they do in the book here, times 0.481 over 104, and it's about 0.049. Okay, so what are we going to do with this? Well, let's take a look at the sampling model for p hat right here. Okay. Now, if we knew p, we have a distribution here. Well, now we know if we did billions of p hats, this is what we learned in the last chapter. If we did billions and billions and billions of p hats, they would have an approximately normal distribution, assuming that they're all the same size and random independent, not too big, not too small, that they would all these p hats, all these hypothetical p hats, would have a sampling distribution that would center around the truth, around p, and sort out according to the 98, 95, 99.7 rule. So we'd have some p hats that were really small, we'd have some p hats that were really big, and then we would have, most of them would be clustered around the actual true proportion of C fans that are infected by this disease. Okay. So, but we don't know what p is, but we're going to use this one sample. Now, the other thing is, we don't have the money, we don't have the resources to go in and expect sample after sample of these C fans. It's probably cost a lot of money and time in order to do this. And while you're doing that, things are changing. So, here's what we're going to do. We know that because the sample from which p hat was drawn is random independent, not too big and not too small, that we know if we go 2 standard deviations to the right, 2 standard errors, I should say, and 2 standard errors to the left, that we are going to cover 95% of the area of the sampling distribution within which all the other p hats would reside. Okay, so what does that mean? It means that we are 95% confident that p resides within plus or minus 2 standard errors of p hat. Now, why can we say this? If the sample is representative, then p hat is drawn to p because it's a representative sample. It's going to reflect p. And according to the normal model, so we know that 95% of p hats, let's look right here, All the p hats are drawn that are representative. 95% of them are within 2 standard deviations of p. Therefore, we can logically conclude that we have a 95% confidence that a given p hat that a given p hat is plus or minus 2 standard. Here's 95%. Let me do this. Here's 95% of the p hats. Let me draw the thing myself. So here's p, and here's 2 standard errors, and here's minus 2 standard errors, and here's 95% of all p hats. This is the sampling distribution. Okay, so we know that 95% of all p hats are within within plus or minus 2 standard errors of p. Therefore, we can conclude that if we take a given p hat and we go plus 2 SEs and minus 2 SEs, that p is somewhere in there. That this interval, this confidence interval of 95%, we are 95% confident that p resides in that interval. It is some specific number in that interval. That's the logic. Okay, so on to the next page. Now, what does this mean? Let's go through a list of statements here that are wrong. Number 1, 51.9% of all C fans are infected. Absolutely not. 51.9% is p hat. Okay? P hat is not p. Now let's remember stuff about p. P, population parameter. It's estimated. It's always estimated. It's never always. Never known exactly. And it is always changing. Okay? Now, p hat is sample statistic. And it is never estimated. Come on, pen, come back. Never estimated. It is always exactly known. And it never changes. For that particular sample, obviously, no 2 p hats are probably going to be the same. Okay, because samples, you have sampling variation. Okay, but we're talking about the p hat for a specific proportion. Okay, so 1 is false. That's a statement. P hat, we know what p hat is. We know that 54 out of 104 were infected, period. It is probably true. That 51.9%. No, we know from sampling variation that it is probably not true that p hat is 51.9%. That p, the population parameter, the true proportion of 51.9%. The probability that it is exactly the same as p hat is very, 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 very low. We don't know exactly what proportion of sea fans on the Las Redes Reef are infected, but we do know that it's within the interval 51.9 plus or minus 2 times 4.9%. That is between 42.1 and 61.7%. This is getting closer, but you can't say you know it's in that interval. Okay, number 4, we don't know exactly what proportion of sea fans on the Las Redes Reef are infected, but the interval from 42.1 to 61.7 probably contains. Okay, we don't know, but the interval probably contains. We fudged twice. That statement is true. Now here's the specific statement you can say. We are 95% confident that between 42.1 and 61.7 of Las Redes sea fans are infected. This is the best you can do. And this is called a one proportion z interval because it's based on the z-score. That is the number of standard deviations to the right or the left of p hat. Okay. Just checking. Pew Research study. Now, this is what you got. You have to turn this in on next class. If it's I period, that'll be Tuesday. If it's D period, that'll be Monday. Okay. JC, number 1. Pew Research study regarding cell phones. Ask questions about cell phone experience. Unsolicited text messages. Okay, have you ever received unsolicited text messages on your cell phone from advertisers? 17% reported that they had. Pew estimates a 95% confidence interval to be 0.17 plus or minus 0.04, or between 13% and 21%. Which statement is correct? Number 1, in Pew sample, somewhere between 13 and 21% of respondents reported that they, well, no, we're not unsure about the contents of the specific statistic that we got, a p hat. Okay, p hat is exactly equal to 17. Okay, and it doesn't change. All right, the confidence interval is about p, not about p hat. So 1 is wrong. 2, we can be 95% confident that 17% of U.S. cell phone users have received. No, that's wrong, because that's stating that the confidence, that's stating a level of confidence about p hat again. The level of confidence is about p, about the population parameter, about the true proportion of U.S. cell phone users that have received unsolicited text messages. We never say specifically what it is. Okay? So we are not confident that 17% of U.S. cell phone users. We don't have a level of confidence about p hat at all. We are 95% confident that between 13 and 21% of all U.S. cell phone users have received unsolicited. That is specifically, exactly, totally right. Number 4, we know that between 13% and 21% of all cell phone users, blah, 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 have received unsolicited. Nope. That does not express a level of confidence. 5, it's totally wrong. 95% of all U.S. cell phone owners have received unsolicited advertising text messages. 95% is the level of confidence. It has nothing to do with the confidence interval itself. Okay, so the only right answer is number 3. All the others are wrong. What does 95% confidence really mean? Well, we can talk about, let me erase this, I didn't really write anything here. Okay, I just explained the answers to you. You can also look them up in the back of the chapter at the end of the questions. Okay, now we talked about the interpretation of the confidence interval. 95% confidence true proportion lies in the interval. Our uncertainty is whether or not that p really is in that 5%, that we are outside the interval. Okay. Now, on the next page, they're going to show 20 confidence intervals. This is a very interesting picture. The green horizontal line here is truth. Okay. And here's 20. Here's the intervals, 20 standard deviations, and the little red dots are the p hats. Now, notice that the first confidence interval here does not contain p. Okay, and here's another one that doesn't contain p. And here's another one that doesn't contain p. Okay, so we have 20 confidence intervals, but let's see, 1, 2, 3 of them don't contain p. Now this is just, these are random samples generated to simulate this test. But you can see that the confidence intervals are all different, okay? But most of them, 17 out of 20, and if you ran this long enough, if you did hundreds and hundreds of simulations, you would end up with 95% of them would be within P. Okay. So what can you say? I am 95% confident that the interval from 42.1% and 61.7% captures the true proportion of C fans on the laceratus reef that are infected. That level that expresses our confidence and our uncertainty about the interval. It does not state the true proportion. So be very clear about that. For example, polls and margin of error. The Yale Project on Climate Change Communication and the George Mason University Center for Climate Change Communication interviewed 1,010 adults, U.S. adults, about America's global warming beliefs and attitudes. The question is, it is standard among pollsters to use a 95% confidence interval unless otherwise stated. Given that, what do these researchers mean by their confidence interval in this context? Well, now this is a different interpretation. If this polling were done repeatedly, 95% of all random samples, and this is usually what's called the interpretation of the level of confidence, as opposed to interpretation. You have the interpretation of the CI, the confidence interval, and then you have the interpretation of the level of confidence. Namely, what does it mean that we're using 95%? Okay, what does it mean that our level of confidence is 95%? And what does that mean? It says right here, 95%. Now you must burn this sentence into your mind and never let it out. Okay, the interpretation of the level of confidence. 95% of all random samples would yield confidence intervals that contain the true proportion of all U.S. adults who believe there's a lot of disagreement about scientists about global warming. Okay? That is the interpretation of the level of confidence as opposed to the interpretation of the confidence interval. I am 95% confident that the interval of, and then et cetera. Okay? So two different things. Now, here is the formula for the confidence interval. All right? And you want to write this down, you want to do something till you remember it, p hat plus or minus 2 times the standard error of p hat. Now this is our confidence interval. It had the form, okay? Now we're going to get a little bit more refined about this. Okay. The margin of error okay, what does the margin of error equal? Well, it's going to equal some number, let's call it n number of standard errors. So n number times the standard error. Okay, n number of standard errors. That's what the margin of error is. And that number, come on, go away. That number is added or subtracted to p hat. So the confidence interval equals p hat plus or minus the margin of error. Okay. Now, if we want to be more confident, we can increase n from 2 to 3 or whatever. But if we do that, as n approaches, number of standard errors approaches infinity, or let's say, here, let's do this the other way. I'll write this in words. As confidence increases, that is the percentage of the confidence interval, your percentage of confidence increases, the CI gets wider. That is the arithmetic interval in which you are estimating that P resides is going to get wider and wider. So you have more confidence, but you also have more uncertainty of where exactly P is. So that's the dilemma. And like this little cartoon shows, the high temperature is between 40 below zero and 200 above. Although I guess recently he might have been wrong in some parts of the country. All right. For example, to do a recap, George Mason University, 10,010 adults, about current topics, reported margin of error of 3%. Now, it is a convention among pollsters to use a 95% confidence interval and to report the worst case margin of error. That is, we talked about this before. The biggest margin of error has a p-hat of 0.5. And you can see this. Here, let's do this. Let's get the calculator out here. Let me show you something on the calculator. Okay, let me clear this. Let's do y equals. Okay, now we're going to do x times parenthesis 1 minus x. Now this is all the possible p's combinations. If you consider p, x to be p, and then 1 minus x is q. And so this function would produce all the possible values of p and q. Now let's set our window up. This will be our domain. We'll go from 0 to 1, okay, because that's where, and let's make this 0.1, okay, and then the y min will make 0, and we'll make it, let's see, I don't know, 0.4, and we'll make this 0.1 as well. Okay. All right. And so you can see if p is 0, then p times q is going to be 0. And if p is 1, p times q is going to be 0. So it's 0 where x is 0, and it's 0, and p and the product is so p times q is 0 when p is 0, and p times q is 0 when p is 1. Okay. And where is it to the highest? It's going to be at 0.5 right here. And let's just prove that to ourselves. If we do a calculation on the max, number 4 here. Okay, and I'll arrow a little bit to the left to make sure I'm to the left of the max, and I hit enter, and I'm going to arrow to the right, and I hit enter, and then enter again, and you can see the maximum is at 4.4. That's the calculator speak for 5. Okay. And that, obviously, that product is 0.25. So if you don't know what P is, and you want to make an estimation, and you haven't taken a sample, or you have a sample, you have a p-hat, but you want to base your estimation of the standard error not on p-hat, but instead on the biggest possible value the p-hat could be, the biggest margin of error, then you're going to use 0.5. And you'll do 0.5 times 0.5. And then use that to calculate your confidence, calculate the margin of error, and then that'll give you your margin, your confidence interval. Okay. Now we're going to get a little bit more refined. Okay. And we're going to bring in this idea of critical value. And note the notation. When we put an asterisk on a letter, it means it's a critical value. So now we have, we're going to change the notation here a bit. The confidence interval equals p-hat plus or minus z star. That's the number of standard errors that you're going to use for your level of confidence. And z star is a number that corresponds to a particular level of confidence. Now, if you go to your book, Appendix F, the tables, okay, and then go to the first table is table of random digits. The next table is table Z, and the next table is another table for Z scores, and finally you have table T. Okay, now we haven't talked to, you don't know what table T is for yet, but if you scroll down to the bottom of table T, you can see here are the z-scores that correspond to various levels of confidence. 1.282 will give you an 80% level of confidence. 1.645, 90%. 1.96, 95%. 2.326, 98%, and 2.576, 99%. Now, so when you want to know how many standard deviations you need to go to the right and to the left of p hat in order to cover a certain area under the normal curve, this is where you go. Or you can calculate it in your calculator, but to do that, you have to do a little bit of thinking. Anyway, the easiest thing is just to look at this table. This table is always available to you when you take tests. And you can just quickly look at the table and get your levels of confidence, your z-scores. So this is the z that goes with 80%, z star, I should say. Z star for 90, z star for 1.96, z star for 2.326, and z star for 2.576. Okay, back to the lecture. Okay, I got to pause for a second. All right, now, for example, finding the margin of error, take 2. So, George Mason University polled 10,010 U.S. adults, found that 40% of the respondents believe that social scientists disagreed about whether global warming exists. They reported a 95% confidence interval. Okay. Using the critical value of z and the standard error based on the observed proportion, what would be the margin of error for a 90% confidence interval? What's good or bad about this change? Okay, well, the standard error is going to be root p hat q hat over n, 0.4 times 0.6 over 1010 square root, 0.0154. Z star, as we said, for a 95% confidence interval, 90% I should say, sorry about that. Let's look at that again. Here we go. Okay. Okay, Z star for 90%, 1.645. Okay. Here, let's click that again. Okay. Okay, so we're going to take the margin of error equals Z star times the standard error, 1.645 times 0.0154, 0.0254. Okay. Now the margin of error is only 2.5%, producing a narrower interval. That's good, but we have less confidence that this interval actually contains P. We're only 90% confident that it contains P as opposed to 95%. So, pays your money, you take your chances. Just checking. Okay, this will also be due next class, 6, 7, and 8. Okay. 6. If they wanted to be 98% confident, would their confidence interval need to be wider or narrower? Well, let's look at the Z star for 98%. That's 2.326. So we would be multiplying the standard error by 2.326 as opposed to 1.645. So, therefore, it would have to be wider, which means we have a bigger area in which we are speculating that P resides. 7. The study's margin error is about 3%. If the researchers wanted to reduce it to 2%, would their level of confidence be higher or lower? Okay. The margin of error gets smaller when level of confidence, here, let me write it out. When level of confidence gets smaller. Okay, they're directly related, okay? Why? Because it's Z star times the margin of error. Okay, they're directly what do you call it? Directly proportional or whatever. Direct variation. They directly vary. If Z star gets bigger, then the confidence interval equals the margin of error. And the confidence interval equals p hat plus and minus the margin of error. So if the margin of error gets bigger, the confidence interval gets bigger. If the Z star gets bigger, the margin of error gets bigger. Okay? So if you want higher confidence, you need a bigger Z star. If you want less confidence, then you're going to get a smaller margin of error, and you're going to have less confidence. Okay? So, lower. Eight. If the researchers had polled more people, would the interval's margin of error have been larger or smaller? Margin of error equals Z star times P hat Q hat over N. That is the standard error. As Z star increases, the standard error decreases. Okay, they're inversely proportional. Okay? Now, so as n, that's the sample size, increases, standard error decreases. As standard error decreases, margin of error decreases. And all you got to do is just keep the whole shebang clear in your head, okay? Confidence interval equals p hat plus or minus Z star times the square root of p hat q hat over n. So you can see if n increases, the whole thing's going to get smaller. If Z star increases, it's going to get bigger. The whole thing is going to get bigger. If Z star decreases, the whole thing's going to get, the confidence interval is going to get smaller. So, smaller. Level of confidence wouldn't have changed, but the confidence interval, the margin of error would be small, and the confidence interval, consequently the confidence interval would be smaller. Okay, assumptions and conditions. No difference. Okay, independence, random. Not too big and not too small, NP and NQ. Okay? And that is it.